Hey everybody, and welcome to McArdle Math Academy. In this video I want to talk a little bit about instantaneous rate of change, what it means, and how we can find it. Let's first talk a little bit about average rate of change. So suppose that we have some function f of x. So that's what I've graphed in green here. That's our function f of x. And suppose we have a point on the x-axis, say x equals a, and we step over to another point a plus h. If you find the 2 points on the graph, I've drawn them in green here, there are 2 points on the graph of f of x, and connect them by a line, that's this orange line right here, that's called a secant line. Now the slope of that secant line is what we define to be average rate of change, and that tells us how the function value, the y value, how the y value changes with respect to the x value. Alright, and we have an equation for that. And that equation is just using the equation of slope. That's the y2 minus y1 over x2, which is a plus h, minus a, and so you just get an h in the denominator. So all that is slope. Now, as we transition to trying to find instantaneous rate of change, what we do is we make this h value a little smaller. So these points are going to travel farther down the function f of x as you get closer and closer to the x value of a. And you'll notice what happens to these orange secant lines. They're going to get closer and closer to the red line that I've drawn in here, which represents the instantaneous rate of change of the function f of x at the value a. Alright, and on the next slide I have the equation for instantaneous rate of change. And so here's the formula for instantaneous rate of change of a function f of x at x equals a. All I've done is taken the formula for the slope of the secant line, and we're going to take a limit as h goes to 0. That's essentially moving that point down on f of x until you get to the point x equals a. And this gets us the slope of the tangent line. So I want to make a note here that this represents the slope of the tangent line. And that is what I've drawn here. This is the function f of x. Let's say you have a function f of x. There's always an x value, x equals a. There's a point on the function at that value, and the line that just grazes the function at x equals a is what we refer to as the tangent line. So the slope of that line is given by this formula right here. And so let's do a few examples so we can see how to compute the instantaneous rate of change. Let's suppose we have a function f of x given by x squared plus 1, and I want to compute the instantaneous rate of change at x equals 2. So down here I've drawn the formula. I've written the formula, and so we have to find a few things. In our case, since we're doing it at x equals 2, that means that our a value is given by 2. So we have to find what f of 2 plus h is and what f of 2 is, of course, before we can input anything into the formula. So I'm going to do that here. And so you can see all I've done is input 2 plus h into the function, so you get 2 plus h squared plus 1. Simplify that out, you get here, and do the same thing with 2 to get 5. So now what's going to happen is we're going to take this blue piece of the function, that's going to go where this is in the formula. We're going to take this, and that's going to go where this is in the formula. And then we're going to see what happens with our limit. So again, you can see the formula here, that's the formula, just where I've written a as 2. And I've taken f of 2 plus h, that's in blue, and f of 2 is in red. Alright, now we can simplify, so the 5's are going to cancel. And we're going to see what happens with this limit. So let me rewrite what we have. When you look at this quickly, you might say, well, we have a problem because we're trying to compute a limit at h equals 0, and there's a 0 in the denominator. Well, this is a rational function, so we have to follow those rules that we learned when computing limits of rational functions, and therefore we need to simplify the top and bottom and see if we can cancel any factors. And sure enough, we can factor a common h out of every term in the numerator to get this, and that's going to cancel with the common factor of h in the denominator. So all we're left with is the limit of, as h goes to 0, of h plus 4. And remember, at this point, we can just directly substitute, so we get a value of 4. After all is said and done, we get a value of 4. That's the instantaneous rate of change of the function f of x at x equals 2. Alright, so what does this mean graphically? Here's our function x squared plus 1. We're looking at the point x equals 2. There's a point on the function at that x value. There's a tangent line to the function at that x value, and this tangent line has a slope of 4, as we just found on the previous slide, and that is exactly the instantaneous rate of change of the function f at this x value. Now, in this same setting, we can check out some application problems. So suppose that the cost function in dollars of producing x units of some product, it could be anything, is given by this c of x equation here. And we're going to do two parts here. Let's suppose we want to find the average rate of change of cost with respect to x, as the production is changed from 40 units to 50 units. So essentially we're trying to find average rate of change of this function on the interval from 40 to 50. All right. So let me write first the equation for average rate of change, and then we'll plug in everything that we know. And so I've gone back to our original equation that we learned for average rate of change of some function between x equals a and x equals b. It's simply f of b minus f of a over b minus a. Well, our f in this case is really cost. It's a cost function. All right, so what we're actually trying to find is the cost evaluated for 50 units minus the cost for 40 units over 50 units minus 40 units. Okay. And those things on top, so obviously we have 10 on the bottom, the things on top we just input into the equation up here and we'll get some value, so I'm going to do that. And so when all is said and done, we get $92 per unit to be the average rate of change when production moves from 40 units to 50 units. So what if we change the question a little bit and asked for the instantaneous rate of change of cost with respect to x, which is the number of units, exactly when there are 50 units being produced? And this is actually called the marginal cost. So let me get the equation for instantaneous rate of change. So that's down in the corner here, and again our f is not really an f, it's our cost equation, and our a is 50 units. All right, so let's compute the two things that we need to find. That's cost of a plus h and cost evaluated at a. Again, a is 50. So if you take cost, the cost function of a plus h, that's 50 plus h, we're going to use the equation for cost on the previous slide, x squared plus 2x plus 1,000. And I'm going to, expand this out. I'm going to distribute the 2 into both these pieces and then combine like terms. We're going to get the following, h squared plus 102h plus 3,600. I can then do the same for c of a. Use the formula, we'll get 3,600. So the blue piece and the red piece are going to come into the formula for instantaneous rate of change, and then we're going to see how we can simplify this. So I need some more room here. Here's the formula where I've written with C's instead of F's. Let me move up, and we're going to take each piece from above. So for the blue piece, c of a plus h, that's what's blue above. That's h squared plus 102h plus 3,600. Let's subtract the red piece, which is 3,600. That works really nicely. And we're going to divide this all by h. Notice what happens to the 3,600s. And we start to go into our simplification mode. So we just try to simplify everything before we can take this limit. Because it's a rational function, we do have a discontinuity with the h in the denominator, but that's okay, because I can factor out a common h on top. So these are pretty long problems. They require a little bit of algebra. So I'm factoring out a common factor of h on top. Both are going to cancel. And so you're just left with the limit of h plus 102. And at this point, we can simply input h to being 0, and we'll just end up with a value of 102. Again, this is instantaneous rate of change, so the units are dollars per unit produced. And that represents the slope of the tangent line to the cost function when x is exactly 50 units. And finally, the last slide for this section, I just want to point out that instantaneous rate of change we know represents the slope of the tangent line. So what this means is that if I give you a graph of a function, the peaks and valleys of this graph will always have instantaneous rates of change of 0. So for example, this valley, the slope of the tangent line at this point down here, whatever this point might be, let's say A, has a slope, an instantaneous rate of change of 0. And the same can be said for this peak. All right, so whatever this point is, say B, that also has a slope of 0. And also this valley and this peak as well. So a lot of times you might be asked for where the instantaneous rate of change is 0, and that simply occurs where we have peaks and valleys on the function f of x. All right, guys, I'll see you next time.